So, yeah, as Lajos said, the title has changed. So I'll say a little bit about why. Detlef originally asked me to speak about how quantum theory emerges from causal sets, which, as some of you may know, is a hypothesized discrete substratum to space-time that's intended as a basis for quantum gravity. He asked me to speak on how quantum theory emerges from it, but I can't actually do this because I don't know that quantum theory does emerge from causal sets. I mean, it is true that a radical non-locality does follow from the two of the basic features of causal set theory, namely discreteness and Lorentz invariance. And this non-locality, I suppose, is certainly suggestive of some sort of route to quantum mechanics, but the type of non-locality in question is, as it turns out, quite compatible with classical screening off, by which I mean the condition that goes into the derivation of the Bell inequalities. So there's nothing forcing you to violate the Bell inequalities coming from this sort of non-locality. On the other hand, I do think that causal sets in particular and quantum gravity more generally do have important lessons for people working on quantum foundations. The main lesson, in fact, the main lesson I have in mind in saying that is that canonical quantization is not a promising starting point for quantum gravitational dynamics, whereas on the other hand, the path integral is a promising starting point. In other words, I believe that quantum gravity requires a histories-based formulation of quantum theory, such as Faye described this morning. So in this talk, all I want to do is illustrate the formulation that Faye talked about, which we call, I think she didn't use the word, but we call it the co-event formulation. I want to illustrate that in the context of a very simple, simplest possible toy universe, which can be called a three-site hopper. So some of this work that I'll be describing is done, in fact, with Faye, with Petros Walden, who's here, and with some other people who are not here, but one of which was mentioned, which was Joe Henson. Also, here there's been a lot of talk, and I think there will be more, and there's a lot of interest in the Bohmian type interpretation. So let me say a little bit that you might find interesting, a way in which what I'm going to describe will contrast with the Bohmian account. Think, for example, of a hydrogen atom. And suppose you took the point of view that what the reality was the trajectory of the particle, and you thought of the wave function as law-like or nomological or whatever this fancy word is that people were using to describe law-like, then you might ask, is there something in the trajectory that carries the kind of information that we need when we talk about something like the energy of the atom or the electron in the Coulomb potential? So would we be able to know from looking at the trajectory whether the atom was in its ground state or in an excited state or so on? Now, I don't know that there's a general answer, but in at least one particular case in the Bohmian theory, we can say that the answer is no. And that's the case of a particle whose wave function in a box, say with zero boundary conditions, Dirichlet boundary conditions, in that case, the wave function is a standing wave, and the phase is constant, and so the Bohmian particle doesn't move at all. It just sits still. Just from looking at it sitting still, you wouldn't know if it was in the ground state or the first excited state or the nth excited state. On the other hand, in the n-homomorphic coevent, which is sort of the full name of this formulation that Faye gave an abstract description of, physical reality is described by what I've called here a coevent, but she described it as, in that particular version, particular scheme as we call it, of the coevent formulation, it's described by, I think Faye called it a coarse-grained history, or in other words, it's a set of histories rather than an individual history. It's not described by the wave function. So the particle, that's very different, of course, from the Bohmian theory, where there is a wave function either hovering in the background or in the foreground, but there's a wave function. Here the wave function plays almost no role, but instead you have this set of trajectories. If we look at that set of trajectories, would we be able to tell if they were corresponding to a hydrogen atom in its ground state or in its excited state? Would we be able to tell which it is? That's what I mean by the title, Does the Quantum Particle Know Its Own Energy? Okay. So I'm going to ask this question. A hydrogen atom is a much more complicated system than we could handle at present. It's an infinite dimensional configuration, an infinite dimensional path space. People even now don't have a good, precise definition of the path integral in general. But let me introduce instead a very simple model that I think carries all this essential, allows us to ask all the essential questions, and I think is actually a model that's of some interest in itself, independent of the foundational issues, which I call the n-site hopper. So this is a particle hopping on a circular lattice consisting of n lattice points or sites. So space is discrete. Not only is space discrete, but also time is discrete in the sense that there's a succession of moments at each of which the particle is at one of the lattice sites, and it's just that succession of which lattice sites that it's at that defines its trajectory. The dynamics is going to be given, of course, by a path integral, but here it'll be a path sum, really. It will be a discrete path integral, and the amplitude associated to the path will, as usual, just be a product of the amplitudes associated to the individual hops that it takes, and it's given by a very, very simple formula, the following simple formula, in which I've used the abbreviation for 1 here. It means e to the 2 pi I. So when I say 1 to the 1 over n, that just means the nth root of unity. And the amplitude to hop from point x, lattice site x, to lattice site x prime is just proportional, it's 1 to something, which is proportional to the square of the difference between x and x prime. They should be regarded here as integers modulo n. Okay. Actually, this particular formula, aside from normalization, says that you take the nth root of unity and you raise it to the power x minus x prime squared. That actually works only for n odd. For n even, it's slightly different. You need a 2n in the denominator, 2nth root. The only case I'll actually look at is the case, get rid of how do I keep away from that? Is the actual case I look at, as I said, is the 3-site hopper. So this will be like a particle hopping on a triangular lattice. And in that case, this formula reduces to the following simple transfer matrix. It's 1 on the diagonal, meaning that the amplitude to stay put at any given moment is 1 up to normalization. Normalization will actually not play a role in this. And the amplitude to hop to either of its two neighbors is omega, where omega is the cube root of unity. There's a version for n equals 2 that I illustrated here, but I won't be using it. But I put it here because it might be familiar to you. For example, it describes a reflection off a half-silvered mirror, for example. So the interesting thing about this model is that this is a completely unitary, as I said, it's a completely unitary transfer matrix. And in some appropriate limit, where n and the number of time steps goes to infinity, it naively at least goes over to the propagator for the Schrödinger free particle, propagator for the Schrödinger equation for a free particle. So that's the model we'll be using, just the 3-site lattice. And within so that's the sort of underlying physical world that we're talking about, in which there's nothing in the world but just these 3 lattice sites and a particle hopping around. And I'm actually going to simplify it even further, almost as much as possible, in order, without getting something utterly trivial, is limit the number of time steps too. I'm going to limit them to be 3. It's actually non-trivial if you limit them to two, but it's a little bit too boring in that case. So within that kind of world, that toy world, we want to ask, what are the possible realities? These co-events, as I call them, but I'll try to avoid using the word because Faye didn't actually introduce it. These sets of histories, or these coarse-grained histories that can represent a reality. So let me very briefly run over what Faye already told you. And this is, so neither of these words I think she introduced, so forget them, but they're the names that we give to that particular scheme that Faye described. And in that scheme, histories, of course, are fundamental. The wave function plays a very subsidiary role, ideally no role at all, if you could go back to the cosmological initial conditions. Physical reality, or in other words, a possible world, is described by a set of histories. Well, here we call a co-event, which says which events A happen and which don't, and that co-event in turn is described by a set of histories, or determined, if you like, by a set of histories. The dynamics takes the form of a path integral.
So are you saying that events that happen are those that contain as a subset that set of events?
That's precisely right.
Okay.
I'll have a picture to illustrate that in a second. So dynamics takes then the form of a path sum, in which psi enters only as an initial condition, which we like to think of as a kind of summary of the past. For example, you've set up experiment, you did some preparation, and that gave rise to an effective wave function to use in the subsequent analysis. So this wave function is really a summary of that preparation, and if we could, at least the hope or the sort of underlying point of view is that if we could run, but not just start yesterday, but start at the beginning of the universe, we would never even talk about a wave function. We'd talk instead about cosmological boundary conditions on space-time and so on, and the fields, or whatever the fundamental variables are. But in any case, so we will use a wave function, but it'll only give us amplitudes to get started, and then it will never be mentioned again. And you'll see exactly how that goes in the particular example. I think Faye did describe in some detail the idea of the quantum measure and how it comes out of the path integral. The word decoherence functional is also used. I don't know if she did mention that word, but some of you here definitely will be familiar with it in relation to the so-called decoherent histories or consistent histories, as Roland, I think, prefers the word. Faye described how we compute this quantum measure, so I won't review that. But the most important thing to take away from the quantum measure is, for this, what we're going to talk about in the rest of this talk, is the idea of preclusion, which arises completely naturally out of the path integral if one thinks of it as some sort of generalization of the idea of probability. The idea of preclusion is that if the measure of some event is zero, for example, an instrument event, then that event will not happen. If it's strictly zero, that event will not happen. If it's small, then you have to worry, well, sort of typically it won't happen. But let's limit ourselves to the case where it's strictly zero, then those events will not happen. So this is one important constraint on what this co-event can be. But we need a second input, which I've called here primitivity. I think Faye may have called it minimality. And it says that we will describe reality by instead of a single history, a set of histories. That's within this particular scheme that I'm talking about, which is the one that Faye also talked about. That set of histories will be as small as possible. It will contain as few histories as possible, consistent with preclusion. So precisely the thing that Roddy referred to, that an event must not have, if an event does not happen, that must mean it must not contain fully the set of histories that describe the reality. So if the set of histories were to become too small, it wouldn't be compatible with this preclusion principle. But we say that it's as small as it can be, it's minimal, subject to that condition. Classically, this is not far from classical physics. classically reality is described by a single history, or if you like, it is a single history. Quantum mechanically, interference produces non-classical patterns of preclusion that in fact that also preclude that classical idea of reality. And I think Fay described about the three-slit experiment illustrating that. So to review this scheme, just in pictures, what we said in words is that a co-event, that is a possible reality, a dynamically possible reality, is defined by a set of histories, which I've called here the support of the co-event. And I've introduced a notation that we don't really need for the, I think, here. So let's just identify the reality with this set F of histories, which is illustrated here in this red circle. What this illustrates is, first of all, which events happen and which events don't happen. So in this picture, the blue circle, A, completely includes F, therefore it does happen, if the reality is that described by F. The purple region here is completely disjoint from F, so of course it doesn't happen. But also the green region, blue, green region, yes, the yellow, B, not blue, is overlaps F, but it does not contain it, so it also does not happen. So the point is, reality corresponds to a set of histories, and if A were a precluded event, this would not be a valid because it would say that A happens. But if B were a precluded event, it would be okay. And the idea is that the support shrinks down as small as possible, consistent with this preclusion principle. So in the context of this scheme, now I want to address this question, does the particle know its own energy? And in the simple case where we look at the quantum measure of the various events is very easy to compute. It's given exactly by a slightly simpler formula than what Fay wrote down. We just need to add up all the amplitudes and square them, and that'll be the measure of that particular set of histories. This comes about because of a particular feature, a theorem that you can prove that I won't prove, which says that if you define the support of a co-event, a primitive support or a primitive co-event, if you define it by the scheme that I just told you, the smallest support that doesn't fall within any precluded event, then you can prove that in a situation where there's unitary evolution like we're talking about, and in a position kind of, I mean, you're talking about sequences of positions, then you can prove that no matter what the primitive co-event is, it will consist entirely of histories that all end at one single point. So in other words, it will not contain trajectories some of which end at the vertex, some of which end at the base, and so on. There'll be one single point. So for convenience, I've taken that to be the upper vertex here. So we can limit ourselves to only histories which end at that vertex. So had we not done that, there were actually 4 moments of time, 0, 1, 2, and 3, that would have led to 81 distinct histories, but because we limit ourselves without loss of generality to histories that end at the vertex 1 here, that's only 27 histories that we have to consider. And here I've illustrated the amplitudes, what the histories are and the amplitudes associated with them. I should say here what my starting amplitude, so let's look at this history, for example. It starts on the lower right-hand vertex, and then at some point, one of its 3 opportunities, it just hops to the top where it has to end up, and in the other 2 opportunities, it sits still. So it's the amplitude for doing that is the product of the amplitudes of sitting still twice, which is 1, the product for hopping once, which is omega, the cube root of 1, and the starting amplitude. That's where the wave function gets in. And now I want to consider 2 different sets of starting amplitudes. One of them is what you might call the ground state. It's not the one we see here. It'll be next. One you might call the ground state in which the amplitudes are equal for just 1, let's say, for all starting locations. So independent of location. The other one is the analog of what you might call a traveling wave of a particle on a circle, in which it's the other possible eigenvector or eigenfunction of the transfer matrix, and the amplitudes just go 1 omega omega squared. Okay, so that's omega squared, since we're dealing with the cube root of unity, is also omega bar, the complex conjugate, and that's how I'll denote it in this picture. So in this particular example I gave, we had one hop of omega, but the starting amplitude was omega squared, and therefore the product of those is omega cubed, which is 1, since omega is a cube root of unity. So any one of these three trajectories acquires an amplitude of 1. And then there's a whole bunch of others. You can work out what the amplitudes are for all of them. Here I've illustrated them. They all work out, because we're just dealing with cube roots of unity, to be either 1 omega or omega bar. Okay? So that's the model we're talking about. Now, what are the primitive coevents, or the possible realities for this world, in which the initial amplitudes are given by this psi plus, this traveling wave, and the hopping amplitudes are given by that transfer matrix? Well, if you went through that picture that I just showed and counted up the different amplitudes that occur with their multiplicities, then you would find that the amplitude 1, this is the one that I illustrated, occurs. Why does this not go? Yeah. The amplitude 1 occurs 9 times. 9 of the histories have an amplitude of 1. The amplitude omega, 6 histories have that, and the remaining 12 have an amplitude of omega bar. Now, to work out what the primitive coevents are, the possible realities, we need to know, first of all, what are the precluded events. So how can we what collections of histories will have 0 amplitude and therefore 0 measure? Well, that's easy enough to see, because the only algebraic relationship among these three numbers is that they all sum to 0. So the only way you can get a collection of histories with 0 amplitude is to have one with amplitude 1, one with amplitude omega, one with amplitude omega bar, or 2 with each, or 3 with each amplitude, and so on. But there's a limit to that. There's only 6 copies of omega. So the largest precluded set we can ever find would have 6 histories with amplitude omega, 6 with amplitude omega bar, and 6 with amplitude 1. So as long as that set primitive support that I called F, that set of histories that represents reality, as long as it has more than 6 amplitudes of either 1 or omega bar, there's no way it can be within a larger precluded set. On the other hand, we say minimality. If it has, for example, 7 histories with amplitude 1, it cannot be within a precluded set. Therefore, it doesn't need anything else, and it shouldn't have them. So it should consist of exactly 7 histories, all with amplitude 1. So that's one set of primitive coevents. If you count them up, there were 9 histories with amplitude 1. We need to choose 7 of them. We need more than 6, so that's 36 primitive coevents. 9 choose 7. In the same way, we could make a primitive support from not 6, but I circled from the omega bar. We need 7 of those, so that's the other kind of coevent. It consists of 7 histories with amplitude omega bar and nothing else. And there's 12 choose 7, or 792 ways of getting that. So maybe I should just briefly stop and see if there's any questions, because that's the key. The rest is just sort of a straightforward calculation, almost trivial, based on those results. So if there, So if there's no questions on that, then I'll continue. So we just found 9 choose 7 plus 12 choose 7, which is 828. So there's 828 possible realities in this toy world. That's a large number, but on the other hand, the number of coevents that there could have been is any subset of 27 histories. That's 2 to the 27, which is roughly 200 million. So it's a much larger number. So still, these conditions are quite restrictive in some sense. let me just illustrate one of them, a particularly nice one. As we said that every primitive support must consist of 7 elements, 7 histories, all with the same amplitude. In this case, I took them all to have amplitude 1. There's 3 of these, 3 which hops, this hops once and sits twice, 3 which hops twice and sits once, and 1 which hops on every opportunity. And an interesting thing to notice here is that they're all hopping in a counterclockwise or a positive direction, which is interestingly enough what you would have expected from the traveling wave that I wrote down. It's kind of interesting to quantify to what extent the set of co-events, the set of possible worlds, manifests a directionality. But I think maybe I'll just skip it and just say that if you look at the whole ensemble of these possible co-events, you'll see that on average there is some tendency to circulate in the positive direction, although it's not amazingly pronounced, and that's kind of what you expect if you only have 3 lattice points. If you really want to see the phase derivative of phase changing, you need a few more lattice points. But anyway, it does show this tendency. Let's now go to, so those are the, I haven't actually shown you which are the primitive co-events except for this one, but they're all made in this same way. And if you would take the time to stare at this set of amplitudes, you would easily work out what they are. Now let's ask the same question. That was for the traveling wave, or what you might call the first excited state. Let's ask the same question for the ground state, by which I mean the starting amplitudes are 1, 1, and 1. All equal, in other words, independent of position. Well, the paths are the same, the histories are the same, but they each now have a different amplitude than what they had before. By coincidence, it turns out, however, when you count up all the amplitudes, you get exactly the same result. 9 amplitude 1, 6 histories of amplitude omega, and 12 histories of amplitude omega bar. Hence, we can immediately conclude, again, that there will be 828 possible realities. They'll be the same sort of sets, numbers of sets. Again, we'll have we'll either have 7 copies of 7 histories with amplitude 1 or 7 histories of amplitude omega bar. But of course, those will be different sets of histories. And so the question of does the particle know its own energy is, I'm going to interpret as how different are those sets of histories. But before we get to that, that'll be sort of basically the end of the talk. But before we get to that, let's go back to the question that I think is interesting in connection with Bohmian quantum mechanics, which is how peripatetic is the particle in its ground state. Remember, in the Bohmian case, it just sits still, doesn't do anything. How restless is it, or how lazy is it in this formulation? So, well, there's an event which says that the hopper never rests at all. What that means is that every one of the histories that goes into making up the co-event never rests, right? It turns out that that event happens in how many? 8 cases. So 8 of the possible realities affirm this fact, that the hopper never rests. In the other, it's not true that the hopper never rests. But it's also never true that it rests that it does rest all the time either, right? That's the sort of, if you like, generalized logic associated with this kind of language that's natural to describing this. But in any case, for 8 co-events, the hopper never rests. For another 28 co-events, it's true that the hopper either never rests or never moves. Strange combination. And for the remaining 792 co-events, the following event happens. The hopper hops twice and rests once. In other words, they're made of, the 7 histories making up that co-event consists of histories that have this property. Each history has the hopper resting once and hopping twice. So in that sense, we could say that the answer is very different from the Bohmian one. The particle is quite restless or quite peripatetic. In some sense, it's taking the trouble to explore its environment, or in the hydrogen atom imagery, it would be taking the trouble to explore its potential in which it's moving. And that's somehow important that it do that, because if it doesn't have the wave function to fall back on to describe the reality. So the only ontology, if you like, or kinematics, as I would prefer to say as a physicist, is the particle kinematics. So let's return now to the main question. Does the particle know its energy? Well, in order that the energy be sharply defined, we really want to talk about an initial wave function that is an eigenfunction of the transfer matrix. So in that case, energy, at least if we had continuous time, energy would have its usual meaning in that case and would be sharp. This is a sort of discrete analog of that. And that's of course why I chose those two initial wave functions. In one of them it's in the ground state, and the other one it's in what you might call one of the first excited states. So asking whether or not the particle knows its energy is asking whether if you have access to the co-event, to the set of 7 histories that describes one possible reality, then if that's all you know, do you know whether we're talking about the ground state or whether this pertains to the excited state? Well, that's really asking. So we had 828 histories, co-events in each case, 828 possible realities. It's really asking how much overlap is there between them. If they overlap quite a lot, you would tend to say the particle doesn't know its energy very well. And that's in fact what happens if you stop time after 2 steps. But with going at least to 3 steps, it turns out that there's no co-event, no overlap at all. So not even one co-event is common to both cases. So in this case, we could say that the particle does, in some sense, completely know its own energy, that it's able to distinguish between those 2 energy levels. Moreover, there's some, I could go through a proof just by exhaustion, enumerating all the cases. That wouldn't illuminate anything. But it's interesting to see what kind of simple events can distinguish the 2. In other words, which events can happen in one case and not in the other case, and allow you to know. So if you know that the particle never rests, if that event happens, then ironically enough, you're in the ground state. We saw examples of those. It's not true for the excited state that the particle never rests. On the other hand, of course, it's also not true that it stays put all the time. That's not true for any of them. Yes?
Clarification. Was there a whole co-event in each of which the particle never rests, or
there were 8.
I forget.
In the ground state, there were 8 co-events such that the particle never rests.
Oh, okay. I mean, if I'm in a co-event that includes some trajectories in which the particle rests and some in which it doesn't,
then we say it's false.
Say it again?
Yeah, then we say it does not. We say it's false that the particle never rests. In other words, in order for an event to happen, the co-event has to be made up of
right. And it's
entirely of trajectories that have that
it's
property.
It's also false that it doesn't.
And it's also false that the complementary event is also false.
So what does it do?
Which, well, here's ask me any question and I'll tell you the answer. That was a stupid thing to say. I thought you might ask about the next election or something. Ask me about any event, whether it happens or not, and I'll tell you. Or if you like, the reality is that set of 7 co-events, and this is a convenient language for referring to that set of co-events. If the particle moves only clockwise, then this is more intuitive, then you're talking about that traveling wave state. If the particle rests exactly once, who knows, but it turns out you're talking about the traveling wave again. And if I were to list sufficiently many things like this, that would give you a unique way of knowing which state you were talking about. So in that sense, we can say, again, that the particle does know its own energy. So I only want to make one final, that's really the end, what, the main thing I wanted to convey, but I want to make one last comment that I think is interesting. It's kind of suggestive in relation to the measurement problem. It has to do with an old paradox that many people here will be very familiar with, which was raised again in the context of cosmology and recently by Daniel Sudarsky. But it's the paradox that suppose a nucleus decays, and then say it's a spin zero nucleus and it decays, then the fragments, the probability of the amplitude for the fragments to come out in any direction has to be the same. So the decay, in terms of a wave function, you have a completely spherically symmetric wave function. Yet you know if you put detectors, you'll find the fragments at some angle and not at some other angle. So what has broken the symmetry? In terms of the wave function itself, it's obviously impossible to break the symmetry. It's some sort of collapse, or it's some sort of Bohmian particle that breaks the symmetry. So what is it in this case? Well, in this case, you can see what happened explicitly. None of these coevents that I showed, these possible realities, share the symmetry. In fact, they all end up at one particular location, so we see immediately that they don't share the symmetry. What shares the symmetry is the ensemble of all possible coevents, all possible realities. And what we see here also is that the wave function is far from determining the possible reality. It puts a strong constraint on them, but it's far from determining them. And we saw in each example that, in fact, there were 828 possible realities consistent with those initial amplitudes. So in the case of the universe, it would be the same story. The one actual reality would not share the spherical symmetry of the initial postulated initial wave function. Okay, I'll stop there.
So just on that last point, but when you say that the symmetry just somehow breaks, but you've put in by hand that the particle ends up at a particular
No, I didn't
lattice.
put that in, but I tried to stress, I didn't have time to stress, but I tried to clarify that that's a consequence. That's a theorem. So give the definition as Faye gave it and as I rehearsed it here of what a primitive coevent is. It's a set of histories that's as small as possible without causing some event of measure zero to happen. That it just follows from that they'll all end up in the same location. And that's fundamentally, it's a consequence of decoherence. It's because no history that ends up at one location will interfere with the history that ends up at a different location, as is probably familiar to you.
So all of your, so you have presumably then everything you've said happens 3 times?
Yes, that's right. So there really are not 828 possible realities. There's really 3 times 828, and but they're all just given from the ones that we saw just by a simple rotation, by a third of a rotation in either direction. So the ensemble as a whole does share the spherical or the rotational symmetry.